Yeah, hopefully you can see my screen. Let's begin. Right. In week five, the material that was covered was the first introduction to the condition number of matrices, sensitivity analysis, operator norm, matrix norm, all these questions. Um, I assume that there are no questions specific to the material that was covered in the lecture. If there are any questions specific to the material covered in the lecture, you can ask me now, because once I start solving the problems, then uh, if something is not clear, it would be awkward to go back and explain the theory in the middle of the session. Yeah, so if you have any questions related to the material of the week, then I can try to uh, help with that. Otherwise, I can jump straight into the problems. Okay, so let's look at the problems itself. Right. So in the first problem, what we given to us uh, is a subspace of Rn V, which is an n minus one hyperplane. And so if you have an n minus one hyperplane, then an n minus one hyperplane uh, is is characterized by this implicit function. So there is a vector u, which is the normal, which is basically normal to this hyperplane, and all points inside V satisfy this property. That it's of course perpendicular to the normal, which means that u transpose x is equal to 0. So basically, x is uh, to write it more precisely, v is basically the set of all x uh, such that u transpose x is equal to 1. Right. We can take u to be the unit normal. The norm of u is equal to 1. Now, if you construct a reflector for with respect to this hyperplane, then the equation of the then basically the linear transform that corresponds to this reflector is given by I minus 2 times u transpose. So this is the reflector for V. Now, what can you say about this? Well, you can say that there's actually an orthogonal matrix. Okay, um, you can check that this reflector, if we call this R is going to be orthogonal. Okay, and so yeah, so now we are asked to find out the condition number of this R. If you have an orthogonal matrix, then what can you say about the conditional number? Well, if you have an orthogonal matrix, um, then what you can say is that norm of Rx uh, 2 is equal to 1, because R is an orthogonal matrix, and so norm of R is equal to 1. This is the 2 norm. If I don't write 2, then it is going to mean the 2 norm only. And Well, uh, what is R inverse norm? Uh, that I leave it up to you to figure out. What is that? The condition number is just defined as this by this. Okay, so that will solve the first problem. Now, coming on to the second problem. Okay, so in the second problem, uh, you are asked to find the condition number with respect to the uh, one norm, right? Uh, well, so again, you have to use uh, this formula. The condition number, in this case, K1 of A is equal to the one norm uh, by A inverse one norm. Okay. So you need to compute the inverse. Okay. But in general, uh, the question is how to compute these operator norms. So let me just write a general statement. Computing uh, operator norms for the one metric or the one norm is easy. And I'll tell you why. Okay. So let's say you are given some matrix B. B is some R M cross M matrix. Okay. So you write this B as equal to some B1 up to Bm. So these are the columns of B. Each Bi is a uh, is itself a vector in Rn. So now you need to compute sup of x1 belonging to 1, um, bx1, right? So that is equal to, so if your x is some x1 up to xn, uh, then this is going to be equal to the one norm of b1 x1 up to bm xn. Okay, this itself is upper bounded by uh, this itself is upper bounded by the one norm of b1 times x1 plus up to bm one norm and then xn. And of course, what you have is that x1 plus up to xm is equal to 1 because uh, because this x is a unit norm and you want to basically compute the one operator norm. Yeah, so notice that sometimes I'm going to use the term operator norm. Just think of the operator norm as the matrix norm. I'm going to interchangeably use the term operator norm also from time to time. Okay, so this is we want to compute the max of this term, which is itself upper bounded by this, and of course subject to uh, each of this. Uh, so this uh, so let uh, yeah so among these columns we want to bm, there is going to be one vector among those columns which has the maximum ith norm, right? uh, so let j be the index uh, such that bj one norm is equal to max of these guys. So basically, bj is the column uh, which has the highest one norm. Then, of course, this quantity is itself going to be upper bounded by bj. Okay. So uh, the one norm, so the one operator norm is actually equal to. So let me just write down the statement. This is uh, equal to the one norm of the column with the highest. Or let me just write it in a precise way. Is equal to the max one norm of the columns. Okay. So you know exactly if you're given any matrix, any m cross n matrix, what is the uh, uh, what is the or rather how to compute the matrix norm for L1 basically. Uh, Now you're given this matrix A, and you need to compute K1A for A and A inverse. Computing A inverse is going to be easy. It's a 2 cross 2 matrix. So you can easily say what is the one norm of A. You need to look at the column which has the highest one norm. So this is the column with the highest one norm. And similarly do that for A inverse. And that's how you will get your K1. Okay, hopefully this is clear. Now let's move on to the third problem. Okay, the condition number represents how susceptible a matrix is to round off errors. Uh, Hmm. Okay, which of the following conditions must be satisfied for P to be an ill-conditioned matrix? Okay, so uh, let me ask you guys this question. Okay, so uh, I mean, if P is a matrix that is given to us, by the way, I think I may have written this wrongly. Uh, Sorry, I may have written this wrongly. So yeah, this is I wrote it as a division. That's wrong. Sorry. Yeah, sorry, I wrote this wrong. Yeah, and here as well. Yeah, please note the correction. I wrote the formula for the condition number wrong. Yeah, sorry for that. Uh, okay. Yeah, so let me ask the question. So, uh, when is uh, uh, P called in condition? When is P ill condition? Let me ask the question. When so there are two options. When AP is small or when KP is large. Can you answer this? Someone?
Condition number is large. When the condition number is large, then we can say that the given system is ill conditioned.
Yes, yes, yes. Right. Exactly. Right. Yeah, that's true. Uh, and so, yeah, I mean, what do we have to find over here? So, you need to compute a delta such that this condition number comes out to be a very large quantity. Okay. Now, now they don't mention you what norm you should take. Don't worry about the choice of the norm. These norms are all in some sense equivalent to each other. Okay, so you can go with the one norm, and you can try to compute this p and p inverse. So basically, you have to so with p it's not a problem because uh, uh, well you have to
Can we
check
use infinity now for that to calculate the condition number?
yeah I think you can I think you can use the infinity norm. I'm still a bit I'm still a bit kind of not sure if these norms are equivalent to each other. um,
Yeah, it depends on the matrix and the normals.
no, I mean sometimes the norms are equivalent to each other. If the norms are equivalent to each other, then I think you can say that. No, well, wait 1 second. No. I think I'm making a mistake. Uh, oh, I think there's a relation uh, between LP and LQ. Uh, in LP and LQ, I think there is a relation. The relation being that um, if P is if P is smaller than Q, then L uh, if P is smaller than Q, yeah, then LQ is contained in LP. Okay. Essentially, it means that if there is something, uh, if you have a set of uh, well, I mean, well, what is LP by the way? I mean, LP is defined in this way for um, LP is basically defined on a class of functions. If we have a collection of functions from a domain to R, uh, right? Set of measurable functions. Oh, I know I'm going on a different tangent, but let's just look at this quickly. Uh, Maybe this is not the right place to write it. Yeah, I mean, I'm looking at some of the material in the course. It's no longer strictly linear algebra. There is there are elements of analysis which one has to understand to progress in this course. That's just how it is. Um,
So please
in general,
text those textbooks in the chat so that
which textbooks?
that
Oh,
whatever
uh,
you
I
can suggest some textbooks which are really
I can
useful for
suggest
this.
that textbook. You can look at this textbook. Jefferson and Bow.
Please maybe suggest
I
maybe two or three textbooks.
Yeah, this is a good textbook. There is one more textbook. Just give me a second. Uh,
Please text with, textbooks which covers the content of this course,
yeah,
because
I guess.
we would I mean
Yeah.
actually, especially I'm planning to do some research on these topics, so that's why.
Oh, I see. I see. Okay. 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 Great.
Yeah.
Yeah. Okay. Fine. Just give me a second. I'll give you the name of another book. Um. This textbook. I don't know if I can share this in chat. Yes, I don't. Okay, let me also write. So I've named one textbook. I'm going to write another textbook. Numerical linear algebra by Gregoire Allaire. Gregoire Allaire and CD Mahmoud. Yeah, you can for now. I think these two textbooks may be okay, but I think uh, as we progress towards the later weeks of the course, I we may have to look at different material. I'm to be honest, even I'm not familiar with the entire material of this course. This is a slightly niche kind of a course, to be honest. I mean, the course is named as Linear Algebra for AI and ML, but it's not really. Uh, it's not really. Uh, it's not really directly where you see this connection between AI, ML, and linear algebra. It's more like numerical methods or algorithmic linear algebra is something that we can kind of call this course. But to be honest, I'm not very familiar with the entire material of the course. For now, I think these two textbooks may be adequate. Let's see later on as we look at some other topics in the course. Then I will suggest alternative. Uh, there are
Okay,
some
sir. Thank
textbooks
you so
mentioned
much.
in there are some textbooks mentioned in the course roster itself. The course page mentions some textbooks. I haven't looked at them to be honest. I think all numerical linear algebra books are kind of more or less they are similar. It depends on some textbooks are more approachable than others. Um, yeah. Okay.
Okay, sir. Thank you.
Yeah, okay. So I mean, continuing on what I was saying is that this is on a slightly different tangent. If you don't, if there are people in the class who don't really get this, it's okay. Yeah, you can skip it for now. You don't have to worry too much. But in general, if you have a measure space sigma, and you look at functions from that measure space to R, then you can define something called LP of uh, this thing. So LP is basically all those functions. It's the set of all functions such that if you integrate this function uh, over this measure space, that's actually more than that. Uh, if you integrate f e, if you do this, then this quantity is finite. Okay. Uh, so if you look at the set of all these functions, we kind of call them as LP. Okay. But to be to be honest, um, well, I mean, LP is actually the closure of all these. It's not really this. LP is the closure of all these guys. So yeah, in general, if you have P to be less than equal to Q, then LQ is contained in LP. Okay, anyway, I mean, how is this relevant? So in our case, uh, so in our case, um, uh, our space is, well, what is our space? So our space can be, um, um, so you can take this space to be the space of matrices, and then you can define a norm. Uh, the norm could be the Frobenius norm, let's say. So the Frobenius norm AF is just sum over I comma j aij squared to the power half. Okay, so so the Frobenius norm is like L2 for this thing. If you appropriately define, if you replace the integral by a sum, it's essentially equal to this only. Uh, right. Um, okay, but the question is, are these norms in general equivalent? So if you write the matrix norm, if for instance, if you have this P norm, and if you have the Q norm, uh, then the Q norm is in general going to be larger than the P norm. Okay. Uh, yeah, the Q norm is going to be larger than the P norm if P is less than Q. So yeah, if something is conditioned with respect to the infinity norm, it's going to be it's it need not, so right. So if something is ill conditioned with respect to the one norm, it will definitely be ill conditioned with respect to the higher norms as well, because that's just the thing. I mean, the higher norms, as we increase p, the higher norms would give larger value. Okay. uh, so yeah, you have to compute p inverse. Just quickly compute this p inverse, and then you can take the one norm. I think you can take the one norm and test with respect to that. But yeah, I will look at this question about the equivalence of the matrix norms. I don't think that equivalent, but I may be wrong also. I'll have to check that. Maybe next time I'll have this question in mind. But hopefully this is clear how to solve this question, right? You can take the one norm because computing the one norm is easy. Computing the sup norm is also, the infinity norm is also easy, to be honest. So yeah, you take one of the choices and see for which you get this to be an in condition matrix. Okay. All right. Yeah, hopefully this is clear how to solve this. Let's look at this fourth question.
So
Uh,
can you define the standard matrix norms, like one norm of matrix, two norms of matrix, and like so that everyone can.
Yeah, so the standard matrix norm is defined in this way. Um, so you are given any kind of a vector space which has a norm in it. So let V be a real, sorry, let V be a vector space over R, is the real value vector space, and which has a norm. Okay, the norm vector space. Okay, so then you define. So if you have any linear transformation from V to R, so I'm talking about general linear transformations. But for V, if V is a finite dimensional vector space, then you can think of this T as also uh, being a matrix. So then you define the operator norm uh, T with respect to the same norm over here. This is defined as supremum over X belonging to 1. So to draw a quick picture, if this is the the unit sphere in that space, you vary X over all the points over this unit sphere, and you compute this thing. Okay, this is known as uh, the matrix norm or operator norm. Uh, Now, just a few quick points. I defined it as a supremum. So generally, the space V, uh, if this space V is a complete normed vector space, which means that if it's a Banach space, then because yeah, if it's a normed vector space, and if this uh, this unit sphere is a compact space. It will not always be compact, but if it's compact, then this will exist, and and it will always be smaller than zero. So if if the unit sphere is compact or equivalent, or if if V is finite dimensional, in which case the unit sphere will always be compact. So if it is finite dimensional, then the operator norm exists and will always be smaller than infinity. It's going to be uh, it's going to be finite. And not only is it going to be finite, because uh, if you assume that B is a complete norm space, so if uh, if B is a complete norm space, uh, such as any Rn, then then they exist uh, then there exists an x at which this maximum would be achieved. Uh, so there exists x star, a norm of x star is equal to 1, such that p of x star is equal to t. So you can actually, so this is actually achieved. So in which case you can, instead of writing the supremum, you can just write as max. So we're going to just write max everywhere because we're going to deal with finite dimensional vector spaces over here. So we're going to just write it as max. Now, what about the one norm, two norm? Well, it just depends upon the choice of the norm or on your vector space. So uh, uh, So what is the one norm? The one norm is defined in this way. The one norm of x is or rather let me just write it quickly. The phi norm of x is defined as uh, xi to the power p plus xn to the power p whole to the power 1 by 2. Okay, and um, and when p tends to infinity, uh, this xp this we call this the the infinity norm, and the infinity norm is just the maximum of all the coordinates. So you look at the coordinate points and you see which coordinate is the largest. So this is just the largest uh, absolute value coordinate. Okay, this is just very simple. Whatever the absolute rate, you just pop it out over here. And so each of the terms would get divided by that quantity. And the rest of the terms is just equal to 1. And they will all vanish to 0 because p is large. So p is going to tend to infinity. So all those terms are going to just drop to 0. And only the largest absolute value coordinate will exist. So in short, if you just give an example, so the L infinity norm of so if x is let's say 1 to 100, then the this would be equal to 100. So it's just the largest absolute value. And the operator norm is defined with respect to this only, right? Uh, yeah, sometimes it is possible that the matrix A need not be a square matrix uh, per se. Um, it can be a rectangular matrix. So in general, you could have the map from some vector space V to some vector space W. Okay, but V and W may have different norms. So V could be this, and W could be this. Okay, and so in that case, you just define the uh, the matrix norm in this way. Matrix norm will be defined as supremum because the domain follows the one norm. So with respect to the domain, you will have to write this. This is not one or two norms. This is I'm just calling the norms as one and two. So don't confuse with this p norm over here. I'm just using the subscripts one and two to distinguish between the two norms on the two different vector spaces. Or maybe just write it. Let me just write it as v, or let me just write it as w here. Okay, so here the v norm, but here the w norm. Okay, it's natural. Tx belongs to w, x belongs to v. So you have to use the appropriate norms. Uh, oh, I wrote t. Sorry, it will be a. Yeah. So this is how, in general, the norms are going to be defined. Uh, it depends on the kind of norms you are imposing on the vector space that you are dealing with. Um, okay. Yeah. Hopefully it's clear.
Sir, I have one query here.
Yeah. Someone asking you something?
Yeah,
Yes,
yes, sir.
please go ahead.
Actually, in some textbooks, I have seen two norm of matrix is defined as sum of
Yeah.
squares of all elements of a matrix.
No, that's the Frobenius norm.
And in some
Um,
textbooks, two norm is defined as
so the
maximum absolute column norm. Which one is correct?
oh, the two norm is not necessarily equal to that. Um, Well, no, no, no. The two norm is not equal to the maximum absolute column. Let's just see what the two norm is. If you have a matrix A, um, first of all, what is the two norm? So the two norm is this, right?
Yes, yes.
Agreed. This is the two norm, right? So what is uh, what is this max, right? So this is equal to. So if you write A as A, if you write this A as A1 up to AN, so these are the columns basically. Then AX, and if you write X as X1 up to XN, maybe I'll use capital letters so that is clear. Then AX is equal to A1 X1 plus up to AN XN, right? Now you take the two norm of this, right? Uh, Subject to the condition that x1 squared up to xn squared is equal to 1. Uh, Now it's not immediately clear uh, what should be the two norm. In fact, if you ask me what the two norm is, the two norm is actually equal to the largest eigenvalue of A. Okay. This will come later in the course at some point. The two norm is equal to the largest eigenvalue of A. And the Frobenius norm is defined uh, as this. This is the Frobenius norm. Um, Now the Frobenius norm and the two norms are actually equivalent. Um, yeah, I think you can show this. I think I read it somewhere that the Frobenius norm and the two norm are equivalent. Um, I think they're equivalent. But I'm not. I don't recall a proof right now for this. Uh,
I think in some textbooks they have mentioned two norm is a maximum absolute column sum and infinity norm is a maximum absolute row sum.
okay. Okay. Can you give me the name of the textbook?
Uh,
Because
Textbooks,
because we
I
will
have
see
seen
later
the,
on.
I don't remember
Uh-huh.
the exact textbooks. Maybe this NPTEL lectures, they use this.
No, 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 no. The two norm, it's a well established result. The two norm will always be the largest eigenvalue of A.
Okay, sir, please go
This,
to
this,
solve the solve. We will take care of it. Please go to
yeah, yeah, okay.
go and solve the problems. Yeah.
Yeah, yeah, okay. Yeah, so yeah, so yeah, you're given a matrix A and you want to make it into an upper triangular matrix. So you will multiply A with some rotator matrix. So it's going to look like something uh, like a typical rotation matrix, like cos theta, sin theta, minus sin theta, cos theta. Uh, you do this 1, 3, minus 4, 1. And when you multiply this, uh, you want this quantity to drop off to zero, basically, right? Uh, yeah. So you would have to solve for uh, yeah. Just make sure that when you multiply this thing, this quantity just drops to zero. And so essentially, you'll be solving 3 cos theta minus sine theta is equal to zero. So you'll be solving for this, and that gives you the value of theta. And from there, you will get uh, the uh, uh, you will get the matrix R2. Okay, and once you have the matrix R2, you just compute the condition number of R2. Uh, that's just how you do it. Okay, these are all computational problems. All right, let's look at the following problems. Yeah, this problem is a very basic problem. So just quickly, I'll tell you the relation between this min magnitude and I hope it's clear what this min magnitude is. This was covered in the notes, I think. Uh, so this uh, uh, so this min magnitude, just so that it's clear to everyone, this min magnitude is defined in this way. Uh, just as the max was defined as the soup.
Actually,
This,
I haven't watched the
yeah.
video still now, sir. Please explain me the way you are explaining.
Okay, okay. So, I mean, uh, the soup norm is defined in this way as soup of x belonging to 1 ax, right? They're calling it as the max magnitude. And similarly, there is this min magnitude, which is defined, and that's the infimum, right? Okay. Now, of course, if A is not an invertible matrix, right? If A is a singular matrix, then this is going to be zero, obviously, because you will have some element x at which you can drop it to zero. Uh, but if it's an invertible matrix, then this is going to be some positive quantity bigger than zero. Okay, and the the uh, the idea is that, not the idea, the small lemma is that uh, this quantity a small m, so capital M for max, small m for min, m is equal to 1 by this. So this min magnitude is equal to uh, 1 upon the uh, yeah, 1 upon uh, the soup norm of the, or the operator norm of the inverse matrix. Okay, yeah. So if once this relation is clear, then you know how to compute k to a. All right. Uh, but what is the proof of this? Uh, uh, the proof of this is basics. I leave it to you to uh, to prove it for yourself. Uh, uh, it's simple. Uh, if you can't prove it, then I can prove it to you in the next class. Okay. Uh, leave it as a homework. Yeah, yeah. This is a good question. Question number six. Uh, By the way, is it clear why we are studying the condition number of matrices? Like, do you have a do you have like a practical no, no, yeah, do you have like a practical scenario why it is important to study uh, conditioning, whether a matrix is ill conditioned or whether it's nicely conditioned? Uh, uh, can you give me uh, can you give me a reason why it's important to study this? Anyone?
I think for practical purpose only, sir. I don't know
Yeah,
exactly.
yeah, but what is the practical purpose?
It depends on the problems in
Okay,
different.
so this is one scenario where this is very important. So when you have a matrix, so matrices appear everywhere in physical applications, like uh, almost almost everything that we do, uh, practical computations, almost everything are linear maps. Everything is linear algebra at the end of the day. Loosely speaking, don't quote me on this, but uh, so matrices appear everywhere, but when you represent the matrix in a computer system, the matrix is not going to be exactly stored. So the computer system would use a certain number of bits. It's going to use either 16 bits or 32 bits or 64 bits. It's going to use a certain number of bits to store the matrix, right? So when you have a real number and you're trying to represent the real number using 32 bits or 64 bits, there will always be some kind of a round off error. You can never exactly represent that real number, or not all real numbers can be exactly represented in 32 bits, 64 bits, and so on, right? And so then what happens is that whenever the matrix is stored in the system, it's always going to encounter some floating point errors, right? Now, the question is, if you perform these matrix computations, you have to understand if these floating point errors that you will obviously incur, you'll invariably incur those floating point errors because that's just how the computer will represent it. Uh, it's important to understand if those floating point errors lead to significant differences in the result. We do not want significant differences in the result. And so it's important to design algorithms which are stable uh, in the sense that these floating point errors do not lead to vastly different results. And this is like a very so people working in doing research in numerical linear algebra and numerical methods and so on. This is a very important area of research. There can so for instance you will see in many algorithms that that compute this thing. So let's say you looked at equation solving. There will be the LU decomposition. There is the QR decomposition. Even in the QR decomposition, you can do the QR decomposition in many ways: rotators, reflectors. You can use something like the Gram-Schmidt orthogonalization to do that thing. But each of those would each of those on paper will give you the same QR decomposition. The QR decomposition is going to be unique only. But the thing is that uh, when you are multiplying many matrices, let's say you're building it using reflectors or rotators, let's say. So then you will you will multiply rotators one after the other until you get the matrix from that form to the upper diagonal form. Now, every time you do a matrix multiplication, you're going to encounter some kind of a rounding error. And those rounding errors, we have to check if those rounding errors get bigger and bigger as we multiply more and more matrices. So yeah, this is the kind of analysis that is often done in these algorithms, which decides which algorithm can be used, which cannot be used. Some algorithms will be faster, but they would not be stable. Some algorithms will be stable, but they would not be fast. And this is uh, this is a very deep area, and it's an area of active research. Unfortunately, I don't know. I only know the basis of this field because it's not my area of research. Um, but I know that this is an active topic of research. So this is why it's important to study this stability. Like what happens if it's like a quarter of the matrix? Because the perturbation actually corresponds to the floating point error that you will incur when you are storing it in a computer system. All right, that was a small detour. Okay, so here you have two matrices. One is this one, and the other is this one. So both of them represent the same equation. Okay, but uh, but you have to say which one is better condition. So if you call this as A1 and if you call this as A2, you need to compute the condition number of A1 and the condition number of A2. Let's use the one norm only. Uh, compute the uh, condition numbers A1 and A2. You will see that for one of them it's quite big, and for one of them it's actually quite small. Okay. Uh, okay. Okay. Maybe not that. Okay. I think this is a question that needs to be. Uh, uh, let's spend a little bit more time on this question. Um, right. So what you want is basically this. Uh, um, if you are given a system of equations which is some ax equals b, uh, let's say you're given upper. Let's say it's an upper triangular system. So you have qx equals b, where u is upper triangular. Um, then the question is, um, okay, so okay, just give me a second. Let's not do go that by that route. Uh, yeah, so you can obtain the solution in this way. You can write the solution as x star is equal to a1 inverse of 10 power 6 comma 1, or you can write x star as equal to a2 inverse of 1 comma 1. Okay. Yeah. So yeah, I mean, the question is slightly ambiguous. It doesn't tell you how you go about solving the system. So let's say you solve the system in a regular way. You just take the inverse of the matrix and you compute this 10 comma 6 and you convert the basically compute the inverses. So then the problem of computing the solution boils down to the condition number of the matrix vector multiplication operation. So you have to look at the condition number of A1 inverse and the condition number of A2 inverse. You have that advantage that if you take a matrix and uh, if you take the inverse, then the condition number doesn't actually change, because the condition number is just defined in this way. So the condition number is same for a matrix and its inverse. So this is just going to be equal to uh, k2 of a1 and k2 of a2. Yeah, so you have to examine the condition numbers of a1 and a2. Uh, uh, the smaller condition number is the system which is better condition, is what it is going to be. Yeah, hopefully it's clear how to solve this. Just write it down. The smaller condition number is better condition. Okay. Um, let's proceed. Which of the following matrix maps each vector in R2 to its reflection with respect to y equals x? So if you have a point a comma b, and if you reflect it, it goes to b comma a. Yeah, so just figure out which of the matrices that system will problem. Right. Okay. Yeah, hopefully this is clear. This is a pretty easy uh, map. The map sends AB to B comma A. Okay. Now look at the ninth problem. Okay, so you're given this system of equations, and uh, Yeah. So in general, if you have uh, in general, if you have ax equals b, okay. So then uh, this is this is a standard well-known fact that uh, that is basically there in the notes only. That when you put up x and when you put up b, then if you uh, note the perturbation to be del b, then del b upon b norm is upper bounded by uh, sorry, is upper bounded by a norm times a inverse norm times the perturbation in x by the perturbation in by x norm itself. Right. So this is just straightforward. This is how we arrive at the definition of the condition. Right. Now, when you're solving a system of equations, uh, you solve x as equal to a inverse of b. Right. So it is basically a matrix vector multiplication operation that you are doing. Uh, and so, yeah, and so uh, you know how delta x by norm of x is related to or to delta b by yeah, and of course you know that the condition number of a is equal to the condition number of a inverse. So yeah, hopefully this is clear how to solve it. This just follows from definitions only. Yeah, so this is about the properties of the condition number. Um, okay. Right. I think the first two properties are very clear. Uh, the first two properties. It's the third property that we need to verify. I think the first two properties are immediate. Uh, so for the third property, if you have two matrices, it suffices to prove or disprove. So let me write it down for here. Prove or disprove that the norm of A is equal to the norm of A transpose. The statement is true or not true based on whether this is true or false. Um, so any guesses whether the norm of A should be equal to the norm of A transpose? Okay, so someone says it's false. Um, yeah, I think this is false. I think you can easily construct a counter example. Um, uh, yeah. What if A is a um, what if A is upper triangular? Uh, what if A looks like this? Say you have a matrix like this: A, B, zeros. Okay. So if you take the transpose of this, you get A zero, E five. Um, Yeah, I think this is false. I don't think this is true. Uh, I can think of conditions when it's true. So, for instance, if A is a diagonalizable matrix, then definitely this is going to be true. Uh, if just let me just write it down for the sake of it. If A is diagonalizable, maybe diagonalizable is not right. I think if A is symmetric, let's say, or then it's obviously this one. Well, there is a particular class of uh, of linear maps which satisfy this property. Uh, A transpose is equal to A transpose A. Okay, there is a particular class of operator, and if you have an operator which satisfies this A transpose is equal to, then one can show that the eigenvectors of that transform or that map would be perpendicular to each other. Uh, so the eigenvectors corresponding to distinct eigenvalues are always orthogonal to each other. And yeah, so for those classes of maps, I think the K2 would be equal. But I think for general classes of maps, this statement is not true. Yeah, I guess. Yeah. I think you should be able to construct easy counter examples to verify that this is not true. You can take this AB0C itself and show that. Mm, so this kind of tricky. I think this could be true also. I'm not very sure. Uh, uh, I think this is true in general. This could be true. I'm a bit confused on this because, um, give me 1 second. Well, no, this statement is actually true as well. This is a true statement, and you need to prove this. But I'm going to state a result, but this result will definitely come later on in the course. So the uh, the two norm of any matrix is defined as this is an expression for the two norm. This is the largest eigenvalue of A transpose A. Mm, yeah. Right. So yeah. Uh, so basically, there's if you have learned singular value decomposition, then the largest singular value of then basically the largest eigenvalue of A transpose A is basically the largest singular value of in a singular value decomposition of A. So basically, the largest singular value is uh, uh, is going to be the operator norm. So this is obviously true for uh, uh, right. So yeah, so the third statement is actually correct, not false. Yeah, hope it's clear. Someone had stated false, but I don't know what reasoning they have. I know it's not correct. I know false is a wrong statement. It is correct. Uh, but yeah, I don't know if they have some proof or they just stated it without proof. Person named NK2 say that it's false. Not sure what was his reason. Okay. Okay. I guess we are at the end then. Okay, there's one more question. I missed that question. Uh, sorry. That's, yeah. Yeah. This is an easy question. You're given a matrix and you ask to compute the condition matrix based on the infinity norm. So let's just quickly check how to compute an infinity, the sup norm of the matrix. Uh, so this is sup x infinity equal to 1, and is- right. So now, if you given any matrix A, if you write it as some A1 to AN, uh, then AX is equal to A1 X1 up to AN X7. Okay. So because the right, so because you require this term to be equal to 1, so each of these xi's uh, themselves uh, can vary between 1 and 0. Um, but you can, but one of the xi's has to be equal to 1. So one of the xi's is plus or minus 1. Okay. So ax, uh, this thing would pick the largest coordinate from among this. Okay. So so if you look at the jth coordinate of this thing, then uh, the jth coordinate looks like this. Uh, it looks like AJ1, but AJ1 is the j comma ith entry of the matrix times x1 plus AJN xn. Okay, so if 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 the jth coordinate of ax infinity, it has to be maximized, so then the it has to satisfy the property that, and let me just write it, the sum of the absolute values of the eighth of the jth row of A is the largest. So essentially, if this is one row, so if this is the jth coordinate of this matrix vector product, and if you look at the ith row, the the ith coordinate would be this, right? So what you can always do is that uh, if a j comma, so if okay, so let's say you want to maximize this sum, uh, and you are free to choose this x1 up to xn, right? Let's forget about the other coordinates. You want to maximize this sum. So if you want to maximize the sum, the way you would maximize is that uh, if if a j comma l is negative, then you set xl as -1. If a j comma l is positive, then you set xl as equal to +1. Okay, so essentially you set xl to be equal to the sign of a j comma l, right? You can choose each of these to be equal to plus or minus one because the norm is equal to one. So so by appropriately choosing this to be plus or minus one, this is how you can maximize this row or basically the jth coordinate. Now this is true for all the coordinates from 1 to n, and so the maximum would be achieved uh, for that coordinate in which the sum of the elements of the sum of the absolute values of the row elements is maximized. Okay, so over here, let's say you look at this matrix. So uh, the first row is 3 plus delta, and the second row is 3 minus delta. Okay, so uh, so the uh, so the infinity norm would be equal to 3 plus delta. Okay. Similarly, you compute the inverse, and you can get the infinity norm or the sup norm for A inverse, and that's how you compute the condition. Yeah, I hope this is clear. How to compute uh, the 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 sup norm or the infinity norm for any given matrix. Just look at the row for which the sum of the uh, absolute values of the elements of the row is maximized, and that is your uh, infinity norm. Remember, for the one norm, you look at the columns. So for the one norm, you look at the column. For the sup norm, you look at the row. So for the one norm, you look at the column for which the sum of the absolute values of the elements of that column is maximized. Is that column. Okay. Uh, yeah. Hopefully it's clear. So I guess we are at the end of the session today. If you have any questions, you can ask me now. Uh, Otherwise, I will end it for today.
Thank you, sir. Thank you so much for delivering this lectures.
Yeah, yeah. Thank you for joining. And just on an aside, um, well, I like I don't prefer uh, uh, being called sir. So this